I'll start off. Today we'll be presenting about this common cycles in engineering. First off, I'll be explaining regarding the Carnot cycle. It is known to be the most efficient heat engine allowed by physical laws. And second law of thermodynamics states that not all supplied heat can be used to do the work. So pretty much is, so Carnot cycle is like you supply heat to the system, but not all the heat will be able to be used for work. It's like when you make a cup of coffee and then you put it in a room temperature environment, some of the heat will dissipate to the cooler environment. Yeah, so, and then most of the application is for thermal devices or thermal machines. The heat pumps to produce heating, the refrigerators to produce cooling, and then the steam turbine used in the ships. And it is also used as a standard of performance of all heat engines operating between a high and low temperature. I'll pass it to Elina.
Okay, so this is the basic idea of the Carnot cycle. So usually what they use is an ideal gas, and it's kind of theoretical, this Carnot cycle. So basically what happens is they put an ideal gas into this piston, let's say. So the expansion of the air is under constant temperature, and then the volume will increase and the pressure will decrease. And then from there, it goes in, that's called an isothermal expansion. So isothermal means that the temperature doesn't change. And then it goes into an adiabatic expansion where the volume increases and the pressure decreases. And the gas is contained in an insulated container and then allowed to expand in vacuum. So the gas here is expanding. After that, it goes into isothermal compression where the where the volume is reduced and then the pressure increases. So reduction in the volume of a fluid without any change in its temperature. And then after that, it goes into an adiabatic compression where no heat is added or subtracted from the air and the internal energy of the air is increased, which is equal to the external work done on the air. And the pressure of the air is more than the volume as the temperature increases during compression. So this is kind of just like a basic idea of what it's going through. Not so much as like, it's just like a theoretical idea of how it will provide energy later on. Okay, let me pass it back to Iqbal for the Rankine cycle. Iqbal.
Hello.
Yeah, hello.
Okay. Hi. Rankine cycle is mostly used in power plants, such as coal-fired power plants or nuclear reactors. And this cycle is mostly in steam engines also, where water is pumped into a boiler at one end and steam is condensed at the other end. As you can see from the graph, it's a PV diagram, ATS, no, I know, TS diagram, yep. And then, it is dependent on temperature difference between heat and cold source. The higher the difference, the more mechanical power can be efficiently extracted out of heat energy. Yep.
Okay. So for this one, the basic idea is actually quite simple, I would say. So liquid goes into a pump and it goes into a boiler. Okay. So the boiler will heat the liquid. Let's say it's water. So it will heat the liquid until the point that it turns into steam. Okay. Then the steam goes into a turbine, and the turbine from the steam will expand and make the turbine spin at like a high rate. And then from there, energy comes out of it. So that's how they provide electricity. And then, of course, there's steam inside, but where will the steam go? So in order to be able to reuse the liquid, the steam goes into a condenser. And then from the condenser, the steam will turn back into a liquid. So by cooling the steam, and then it goes back into the pump and then back into the boiler. Understand? Okay. So yeah. Next we'll go to the Kalina cycle.
Okay. The Kalina cycle was developed by Dr. Alexander Kalina, and it uses a solution of two fluids with different boiling points for its working fluid. It utilizes an ammonia water mixture as a working fluid to improve the system thermodynamic efficiency and provide more flexibility in various operating conditions. It can improve an efficiency of a power plant by 10 to 50% of the Rankine cycle, depending on the application of it.
Okay, so I know it looks like a lot, but it's somewhat similar to the Rankine cycle. But as you can see, so this is the boiler, this is the turbine, this is the condenser, this is the pump. So there's two extra things here. There's a recuperator and a separator. Okay, so now this heat also, instead of using a fuel-based heating system, you can use either geothermal brine or heat sources from factories like from cement manufacturing, steel mills, and petrochemical refineries, all that. So when the water and ammonia is heated, again, it becomes a steam and goes into a turbine. And then the turbine will spin from the steam expanding, and then it goes to a dynamo, which will provide electricity. And from there, okay, let's ignore this recuperator first. So coming out of this will be 70% of ammonia and 30% of water. So if you can see from this graph here, it would take a lot for the vapor state to go back into liquid state as compared to if it was a smaller concentration. So to fix that, this separator here is put in so that it will separate the high concentration ammonia. So 30% over here will mix with the 70% coming out from here and make 40%. So inside the condenser, only the ammonia concentration will only be 40%, which will make it faster to turn back into a liquid state. Okay, so that's what the separator is for. And then since coming out of this is very hot steam, right? And this steam is going to be cooled down. So this part also, so this is going to heat it up, heat up the liquid, the solution. So since this part needs to be heated up and this part needs to be cooled down, so this steam here, the heat from this steam, they will somewhat try to preheat the liquid from here. So it kind of like pre-cools and preheats at the same time. And then only it goes into the condenser. So that way, it makes it much more thermally efficient. And the difference between this and Rankine cycle, as you can see here, so this is like the temperature rising, and then this is the phase change. Then this one is the part where it becomes a vapor. Okay, so as you can see, Rankine cycle, when it goes through a phase change, the temperature does not rise at all. But in the Kalina cycle, you can see it rises. So that's what makes it more thermally efficient. So the temperature is constantly rising rather than like having a stagnant point. Yeah, so that's pretty much the basic. Any questions?